So, well, yes, I'm just giving a brief insight on this LIFE Biogasnet project. It's a LIFE project who started in 2019, and what I'm trying to show here is just a few results. I presented the project in, as you said, in another event organized by Finnova. So thank you very much for inviting us again. And I'm just going to show some results on the project. Some interesting results. I'm not going to explain so much about biogas. Everybody here, I think, that knows what's biogas, how it's produced, and basically here I'm talking about the impurities that contain biogas, and more in detail about H2S, about his hydrogen sulfide, which is a very corrosive compound, which is a very an annoyance of in the use of biogas. H2S can be removed by physicochemical technologies, but in our case, we have been developing these technologies. Another technologies based on biological pretreatments. So it's obvious that a previous visualization step is needed for biogas recovery when you burn this biogas in a CHP unit. I mean, this H2S must be removed previously in order to ensure a proper operation of this CHP unit. Our biological systems are based on the presence of a biofilm, where the biogas, the contaminated biogas with H2S is or this component H2S is removed, is oxidized to either elemental sulfur or sulfate. This is a previous prototype we had installed in Manresa, in the wastewater treatment plant of Manresa. This is a biotreatment filter operated for the removal of H2S and using air. This is oxygen as an electron acceptor on the system. But sometimes things do not behave as expected. So after half a year of operation, we have this elemental sulfur accumulation, which is caused obviously by the low solubility of oxygen in water. So this produces accumulation of elemental sulfur. So we decided to test to start studying another technology. The idea is to substitute this electron acceptor, this oxygen, by either nitrate or nitrite. Nitrate or nitrite can be used also as electron acceptor for the partial oxidation of H2S to elemental sulfur, or to the complete oxidation to sulfate. So with this procedure, we don't have more gas liquid mass transfer limitations, because we don't have to transfer oxygen from the gas to the liquid phase. We are just using an already dissolved substance, it is nitrate or nitrite, for the process. Another interesting thing for the plant operators is that we are not using oxygen to methane. Adding to the fuel. If we add the oxidizer, this is not really a nice idea in terms of security. But the possible main drawback here is that we need a nitrogen source. But as you will see later, this is not a drawback, this is an opportunity. So our main objective in the project is to demonstrate a new cost-efficient and low carbon footprint technology for biogas upgrading, reducing the carbon footprint and promoting the circular economy. For this talk today, I think that the most important outcomes of the project are a waste reduction, more precisely the reduction of leachate produced in a landfill, and the raw materials recovery from wastes, more precisely the recovery of elemental sulfur from this H2S. Okay, we have been operating the prototype in Cádiz, in the complex of Miramundo Los Ardales, where it is the landfill the biggest landfill in the Cádiz province. And there we installed the prototype with these elements: a nitrifying bioreactor, which collected some landfill leachate to produce our nitrogen or nitrate or nitrite for the sulfur oxidizing nitrate reducing system. Here we are using landfill biogas. We absorb H2S to the liquid phase, and then we produce elemental sulfur and gaseous nitrogen. Nitrogen is obviously not a problem. We can emit as much as nitrogen as we want to the atmosphere. And our main products are clean biogas and elemental sulfur. This is an actual picture of the prototype, the basic elements. I think the nitrification bioreactor is kind of 1 cubic meter, and also the sulfurization step is also a bioreactor of 1 cubic meter. It's a bioscrubber, in fact. Well, and some few results. As I said, we have been operating this prototype here for 1 year. This is the amount of lithiate we have been treating. The maximum amount of lithiate treated was this almost 0.6 cubic meter per week. You might take into account that this is just a prototype. We are not treating all the biogas in the system, only just a part of it. And this is the production of nitrate, or the oxidation rate of ammonia for our system, which gave us this possibility to treat this 50 cubic meter per hour of biogas with a concentration of 245 ppm. In fact, we didn't reach this inlet concentration. We had lower concentrations than that, but this means that our removal efficiency was even higher than 95%. And regarding the sulfurization step, again, we have removal efficiencies, average removal efficiencies of 80%, but with peaks of 98%. We can reach a stable operation of 98% of H2S oxidation elimination, and the elimination capacity is this value, which is the most meaningful value for the prototype scaling up. This elimination capacity was kind of 9 cubic grams of H2S per cubic meter of reactor an hour. Maximum value here testing was 20, but at the lab scale we have reached almost 120 grams of H2S per cubic meter per hour. So this can be pushed much forward. All right. Also, we performed some experiments trying to test the limits of the technology, and in feeding chemical sulfide, we reached again removal efficiencies of 98% and elimination capacities of 60 grams per cubic meter per hour. This is a very nice value from an industrial point of view, but we still think that we can push forward this value. Also, the production of elemental sulfur was not that high. Only 60% of the H2S was oxidized to elemental sulfur. This is a matter just of the control system. We need to reach a specific ORP on the prototype and keep this value. And this is it's a bit complicated, but we are still working on it. So now the prototype will be moved to Athens to another landfill, which is probably the largest landfill. The largest cogeneration plant in Europe, and we will try another different configuration of the system. The main difference is that now we are using, as nitrogen source, we will use composting exhaust gases, which are rich with ammonia. So we need a first absorption process, then again the same nitrifying bioreactor, and then we will use here a biotreating filter instead of a bioscrubber. The main products to be obtained here will be clean biogas again and ammonium sulfate as a byproduct that the owner can put into market. Well, just some take-home ideas. For me, the most interesting things is that the anoxic desulfurization avoids these mass transfer limitations of the aerobic process. We have reached very low H2S concentrations in biogas, and so we think that the Biogasnet technology is very promising, and because it couples this liquid and gaseous waste reduction while obtaining raw materials. And that's all from my side. So thank you very much for your attention. And yeah, these are our website, my email, and any doubt you have, any more detail you need, just let me know. Thank you very much.
Thank you, Xavier. I'm not sure if anybody may have some questions right now. I know we are a little bit out of time, 10 minutes, but we can still use the maybe 5-10 minutes to interact. I just wanted to ask you, Xavier, well, this is a question for you and also for all our speakers, participants, if with the results that you have obtained in these projects, if you are thinking maybe of presenting for the next LIFE or Interreg or maybe Horizon programs. Do you have it in mind?
I don't think so. That I think that this you know, this project is almost ready to be scaled it up and installed in fact we are planning to install it maybe in Cadiz or maybe in Athens. We have some interest from companies here in Spain and Greece, but I think that yeah, maybe it would be a good idea to contact with somebody who is treating CO2 from biogas, you know, to join our technology with another one to remove CO2, just to, you know, to upgrade this biogas to a better composition, you know, upgrade this biogas until you can put this biogas into the grid or use as fuel for vehicles, whatever. You know, we are just sorting out the problem of H2S, but still there's a 35% of CO2 there. We are not doing almost nothing with that. And maybe perhaps this will be another, you know, another possible new project. Yeah.
If I may, yes, no, quite interesting. We are working in a project that is that tries to capture the CO2 in the also for feeding algae, bioalgae. Okay, perhaps if you could be interesting, we could talk after, Javier.
Oh yeah. Yes.
And
sure.
Also, if you are going to do in Cadiz or in Greece, think about in the next generation projects or structural funds, because it's easier than a LIFE, it's more funding, and you have this project as a best practice to implement it. Then congratulations, it's quite interesting. And also you could be inspired from the global Omnium strategy in the because eco-digestion 2.0 is the second LIFE. They did a first LIFE. With the results, they realized that they needed more time and to do all these tests, to do all this hybridation of the pig slurry with the organic waste in the digesters of the depuration water treatment plants and of the digital and the digital twin, and is what they are doing at the moment. Okay, why not? If you have identified that new need about the CO2, why not to do a new LIFE, and if I may, in the sub-program climate change and mitigation, because you are capturing CO2. And one of our speakers in this roundtable, representing the sector of algae, they could be interested in, I don't know, we could work together.
Yeah, sure.
Okay.
Okay.
Congratulations, Javier. Quite inspiring.
Thank you very much. Thank you.